Good evening and welcome to today's lecture, CSE 213, and we are looking at algorithm and its complexity. You will recall that in the last class, we had a lot of hands-on attempts on understanding the growth of these functions. Our emphasis was especially on understanding the asymptotic notations and their growth rates. Today, we'll provide a quick review of what we did in the last class. And we'll now go to the main emphasis of the day, which is understanding the strategies in knowing and solving problems about growth of functions. You will recall that in the last class, we tried to understand the growth of functions by studying the algorithms and characterizing them according to their efficiency. We told us that this approach is referred to as understanding the asymptotic running time. We were able to draw clear emphasis between the asymptotic running time and the exact running time. And of course, we told you that there must be a way to develop an algorithm that understands the growth of these functions. The asymptotic notation, as we told you, gives us a method for classifying these functions according to their rate of growth. And our last class, we shared opinion about the big O notation, the big theta notation, and the big omega notation. We told us that when you have a function f of n that is equals to the big O of g of n, where there are two positive constants c and n naught, such that f of n is always less than or equal to c of g of n for all n greater than n naught, we say the big O notation exists, and it means that n increases at a ratio that permits f of n to grow no faster than g of n. And that gives us a simple line of statement for understanding all of the big O notation, that g of n is an asymptotic upper bound of f of n. We looked at some example and we went to the big omega notation. In the big omega notation, we use the same number of symbols, f of n, big omega of g of n, c and n naught, to understand that f of n is equals to the big omega of g of n if and only if there are two positive constants c and n naught, such that f of n is greater than or equal to cg of n for all n greater than or equals to 0. And we explained in that last class that if you look at what you have in the big O, you see that the big omega is like a converse of the big O. So, of course, all the actors in this, the functional actors, are non-negative. And this gives us a statement of confidence that as n increases, f of n grows no slower than g of n. If you remember, the last statement for big O is that f of n grows no faster than g of n. So in other words, we say that g of n is the asymptotic lower bound of f of n. We completed that session by looking at the big theta notation. And this big theta notation does not say f of n is less than or equal to big O of g of n, does not say f of n is greater than or equal to big O g of n. It says f of n equals to theta g of n for all three non-negative constants, C1, C2, and N naught. And we explained to you that C1 g of n is less than f of n, which is less than C2 g of n for all n greater than or equals to 0. So, and we gave some assignment to understand that paradigms. So I will expect you to go to the library and study the following. You must understand the arithmetics of big O, the arithmetics of big omega, and the arithmetics of the big theta notations, with emphasis on the transitivity with emphasis on the transitivity, on scaling, and the sum of these functions. So it means that you, on your own home study, you must understand the arithmetics of big O, the big theta, and the big omega. You must understand the transitivity, that is the transformation, how the function grows from one type of notation to the other, and the rate of growth. You must understand the scaling. When you introduce a k, what happens to the growth of that function, and what happens to the upper and the lower bounds. And then you must understand how to add, that is, find the sum of these two functions. So if you have f1 of n as an element of big O g1 of n, and you have f2 of n as an element of big O g2 of n, then that can imply that f1 plus f2, because they are all the constant of n, is an element of big O, the maximum value of g of n, g1 of n, comma g2 of n. That is the experimentation that we will be carrying out on the arithmetics of big O, the big omega, and the big theta. Today, our area of focus today is actually on the strategies. And what we want to understand is the strategy for understanding and growing these functions. I have shared my screen, and obviously you can see what we are talking about. The strategies for big O is the strategy that we'll start with. We're going to look at the strategies for all the three notations, then we look at some assumptions, then implementations, and then we close up the class. Now, we want to look at what we do in a way, how we can stylishly solve this problem. We understand that there is a relationship between f of n and big O of g of n. Of course, if you say f of n equals to big O of g of n, it is very easy to prove, because all you have to do is to put the c, which is the constant, and you find the sum as the sum of the positive coefficients of f of n. And that was what we did when we were trying to say that f1 of n plus f2 of n will be an element of big O of the maximum of g1 of n, comma g2 of n. So what we do is that we ignore the negative coefficients, and that is obvious, because if you assume the negative coefficient exists, then the proof by induction cannot hold. So look at an example here, and you see how we have used the coefficient to make the proof. This is f of n, 5n squared. All of this is f of n. So we are proving that f of n equals to big O of n squared. That is the meaning of this question. That is the meaning of the highlight. So we are saying that f of n squared plus 3n plus 20 equals to big O n squared. We know that we say that for f of n to exist, there are positive constants. So this is a positive constant 5, this is a positive constant 3, and this is a positive constant 20. If you pick all of these are values of c, and n square, and the n square is the highest, has the highest power, the polynomial rate of growth of this expression. Now, when you have c will be for this f of n, the c is going to be a maximum of 5 plus 3 plus 20, which is 28, because you have 5n squared plus 3n plus 20 equals to n squared. So if we pick c equals to 5 plus 3 plus 20 equals to 28, then we can comfortably say that if n is greater than or equals to 0, then n can be equals to 1. It is obvious here. That is going to be the first assumption. That is, please note that this is an assumption. And when it is an assumption, It's an assumption. And when it's an assumption, what it means is that you can tune it. You can tune your assumption depending on the operation you are trying to process. Now, we see that if we have this 5n squared, this is the highest power in this expression, in this function. This is the highest power. It means that your big O of n, your big O of g of n cannot grow higher than this rate. So it means that let us look at the factor, the constants that affect the growth, that propagates the upper band. So that is why we say the highest that can occur for big O of n square, because this n square is what? G of n, remember. So where if you want to re-express this now, you say f of n equals to 5n squared plus 3n plus 20, while g of n equals to n squared. So this is f of n equals to big O of g of n. So you remember we are still doing the same thing. And now, so you now plot all of this back to the initial expression that we have. So if this is f of n, so we know that this f of n will be less than or equals to this expression. Why is it less than or equals to? This is n squared, n, and this is, there's no n here. N raised to power 2, n raised to power 1, and n raised to power 0 here. So when n is raised to power 0 is 1. So 1 times 20 will give you 20. So it's less than 5n raised to power 2 plus 3n raised to power 2 plus 3n. So all of this is less than this. And of course, which is less than 28 raised to power 2. So if you get the expression now, if you get it, somebody just said you cannot hear me because I muted everyone. Muting is not allowing you to talk. It does not affect what you hear. You can hear me. If you have problems about hearing, the video of this will be available then, and I will make sure that you see them. But if you have problem about hearing, all you have to do is remove yourself and join again. I can know how many people are seeing me because I'm hosting this, and I think we are in good order. So therefore, what we have is that we have all of this expression equals to this, because we have been able to show it from what we have in f5 raised to 5n raised to power 2 plus 3n plus 20 less than or equals to 5n raised to power 2 plus 3n raised to power 2 plus 20 raised to power 2. So what we have is therefore a good expression to validate our system. So this is not always easy as we have done it here, because if you have a situation where you are talking about log of n, it might be difficult for you to prove as it is here. But alternatively, we have a functional table that shows the rate of growth. So generally, what we are simply saying is that once we have the values of C and N naught and they are functional, then it is easy for us to prove about the growth of the big O. And this is the last session we are going to cover today, strategies for the big omega and the big theta. So if we want to prove that f of n equals to the big omega of g of n, you know we need to quickly remember some things, that we must have a C that is less than 1. And this is obvious from the expression we had earlier. I have not told anybody to send their matric number as attendance. I'm not going to use that. I'm going to use my screen recording as attendance. Now, going further, you know we are talking about strategies, and I have given you the strategy for the big O. If you look at the strategies to pick a value of C that you think will work, and that's why I told you earlier that whatever you choose for C is an assumption, and you can tune it in a way that you will be able to fulfill the proof. Of course, what helps here is that is why in the beginning of this course, we first of all taught you about mathematical induction. You must know that when you have a value and an expression is true for K, how far is it true for K plus 1? And that is what we are doing where we said that we will need a little algebra to help you do the tuning. So we can often simplify by ignoring the terms of Fn with the positive constants. Why do we have to do so? The theorem below shows that if f of n equals to theta g of n, if it exists, then that will only hold if f of n equals to big O g of n and if f of n equals to big omega g of n. So if we apply these two previous strategies we have discussed, you will find out that we can prove the big OG of n, the big theta g of n, and the big omega g of n. So this is an example that you will take home as assignment number 3. 1 over 2 n square, half n square is not 1n square, not 2n square, half n square plus 3n equals to theta n square. You are going to show that f of n equals to theta g of n, where f of n equals to half n square plus 3n and g of n equals to n square. We have the proof, but we are not going to show you the proof and until you do your own part and we take it from there. So quickly before we go, let us look at the asymptotic bounds and algorithms. If you notice that all the examples we have done so far, we have assumed, and you remember I keep talking about the word assumption, assume that we know the exact running time. But if you also remember the first thing I mentioned in the class where we began this lecture, what I told you was that you do not have the exact running time. The approximated running time is what we call the asymptotic running time to help us to predict and understand the growth of functions. So in general, one way or the other, it might be very difficult to determine the exact running time. But what we do is that we do not need to determine the exact running time. We create bounds without computing the exact running time. Let me tell you, for example, when you were coming for this class, you know that your lecturer you don't know how long your lecturer will stay, but you know one thing for sure, that your lecturer will not be in this class till 12 midnight. So you have created an upper bound, and you know that your lecturer will not come into this class before 9 p.m. You have created a lower bound. So we don't know the exact time that your lecturer will stay in class, but you have the understanding of the maximum and the minimum, which you call the bounds. You want to go to the market. You don't know the price of a commodity, but you know it cannot be more than X naira, and you know it cannot be less than K naira. So you have an upper bound and a lower bound to understand, to implement your understanding. So now the next level we'll go to is that we will look at the complexity of an algorithm. We'll look at the complexity of an algorithm, and this is quite simple. If you look at the first expression that tells you about the state of I, then you know that I is less than n, then this I increases. Then same applies for j, and j also increases. So when you have an array of I and j, you understand that their incremental factor of x will be determined if you have this expression as stated here. Then if this exists, then the highest possible complexity for this expression is big O of n raised to power 2 from this expression. So that is so clear. So we'll be seeing more of that, and that is all we have to do today. It is a very experimental framework. That is, you still need to go back and put examples, so many functions into practice and see how they operate. It is about tuning and understanding the basic framework. So when you understand the basic expression as we have been told, you'll be able to apply them in all the case studies that have been, that we have experimented and shown as examples in this lecture. I hope you understand this lecture. I will be available for questions and answers and comments and suggestions so that we can move forward. I will announce the next class. I have told you we are going to have a marathon of a week, 7 days class at this time every day. So we are supposed to be prepared for that. And I'm sure that at the end of it all, we'll have done justice to discuss.